Okay, welcome everybody to Sustainable Composites, the Future, our summit. We're very, very delighted to have you here. We would have been doing this as an in-person event, but unfortunately, because of COVID, we had to do it virtually. The organisation of the event has been a collaborative effort between two institutes at the University of Bristol, the Bristol Composites Institute and the Cabot Institute for the Environment, and also the National Composites Centre. We've got over 300 people registered to attend. We're not anticipating any technical problems, but this is the first time we've run an event like this, so please do bear with us. We have a 2-hour session today with 3 speakers. And there'll be an opportunity for questions following each speaker. But please use the Q&A, use the chat box to ask questions, and there'll be a panel Q&A at the end as well for anybody wishing to ask any questions at that point. So please use the Q&A function to ask questions. I'll keep an eye on this, and we'll ask questions on your behalf at the end of the speakers' sessions. Now, note that you can actually upvote questions that you'd like particularly to see being asked. And I'll just remind everyone that where we have speaker permission to do so, we are recording this event, and we're also live streaming on YouTube. And the recordings will be made available on the event page shortly after each session ends. So without further ado, I'd like to introduce our first speaker who's opening the event. It's Professor Hugh Brady, the Vice-Chancellor of the University of Bristol, and he's going to open the event for us. So over to you, Hugh.
Thanks, Steve, and good afternoon, everybody. As Steve said, my name is Hugh Brady. I've had the honour of serving as Vice-Chancellor now for approximately 5 years, and as you can imagine, certainly this last term has been by far the most interesting. I hope you've all managed to stay safe during the pandemic. We had, of course, been hoping to see you all in person, but we're delighted that the event is still able to go ahead online. Indeed, as Steve mentioned, it looks from the number of registrations that being online has certainly had an advantage in making the event more accessible. And we're really pleased to see the level of interest in the event, not just from across the UK, but indeed across the world. Sustainability is a top priority for the University of Bristol, so we're delighted to be able to host the event in partnership with the National Composite Centre. The university was, I think, the first higher education institution in the UK to declare a climate emergency, and through the Cabot Institute, the university brings together over 600 experts dedicated to protecting our environment and identifying ways of living better with our changing planet. As most of you attending will know, the Bristol Composites Institute has perhaps the largest university composite materials research activity in the world outside of China, and has world-leading academics working on sustainable composite materials, manufacturing, and structures. And in parallel with that, the National Composite Centre is known as a world leader in industrial research on composites and works closely with the Bristol Composites Institute to deliver real-world solutions. Over the next 5 days, you'll be hearing a series of what I hope are thought-provoking talks from international speakers, policymakers, industry leaders, international, UK and University of Bristol researchers. I hope you have a stimulating week, and that you have an opportunity to visit Bristol in person in the not too distant future. So enjoy the conference.
Thank you very much, Hugh. So I'm just going to start my video again. I'm going to now give my presentation, which is the opening presentation for the conference. So I'm Professor Steve Icorn. I probably should have introduced myself at the start. Sorry about that. I'm from the Bristol Composites Institute, and I'm going to be talking about sustainable composite materials. What are some of the challenges? So just bear with me while I start my talk. Okay. So, sustainable composite materials, what are some of the challenges? Well, just to start off though, I thought I'd give you a little introduction to our conference. As I've already said, it's being run by the Bristol Composites Institute, the Cabot Institute, and also the National Composite Centre. We're running all week in the afternoons of this week, pretty much from 2 till 4 or 5 o'clock. And we want to really challenge ourselves about how composite materials can help us to achieve a net zero carbon world. And how can we innovate to ensure that composites are recycled and reused? And what are the emerging opportunities to improve our social, environmental and economic sustainability of the industry? There's a link down here which you can go to. We've got a number of guest speakers today and for the rest of the week, but on Friday we have Nadeem Zahawi, who's the Minister for Business and Industry, coming to talk to us. And we also have Jane Nicholson from the EPSRC, the Engineering Physical Science Research Council, and Mark Gillen, who's the UK Chief Technology Officer at Innovate UK. And so, our biggest challenge. So what is our biggest challenge? I thought I'd focus out really, rather than in, on composites to start this. And of course, our biggest challenge is us. This is it. We have Earth, planet Earth. I know Tony's going to talk a little bit more about this. In 1996, Richard Smalley, who was won the Nobel Prize for Chemistry in 1996, around about that time, he came up with a top 10, if you like, challenges that we're going to face in the future. And these were energy, water, food, environment, poverty, terrorism and war, disease, education, democracy, and population. And who would have thought, you know, many of these things are challenging us today in the world, and actually they intersect with composites, and composites can help, but they can also hinder some of these issues. And I think these are the things that we ought to be thinking about globally, and composites ought to be thinking in a global sense. Of course, we've had climate change, and we have climate change is a very, very near and present threat. COVID-19 just recently, continuing to be a threat. Financial crashes in the world. This is an ever-present threat to the world. Racism, we've just had the Black Lives Matters, but actually I want to talk about this later in context of climate change, because it's not unconnected. And cyber attacks as well. I've just picked out a few things. These are big issues for us as a global community. But what about the challenge technically? Well, the big challenge really is energy. And there is enough energy hitting the Earth from the sun every hour to supply the world's energy requirements. And actually this energy becomes embodied into plants, which of course degrade over millions of years, resulting in oil deposits. And of course you get minerals and other components have their embodied energy too from the sun. And heat transfer in the Earth's atmosphere generates other forms of energy, which I'll talk about later. But how do we harness this energy? How do we capture that? And more importantly, I'll talk about embodied energy in composites. But of course, all of our energy comes from the sun, ultimately, wind, solar, tidal, and so on. It all comes from the sun, ultimately, and it's just being able to capture that that's the real key. But actually, the real challenge, I think, is what you call exergy, and this is like the useful energy, if you like, or it's a measure of how far away from equilibrium we've gone. And if we look at this very simple process here that we've known about for many, many thousands of years, iron extraction. So we take iron ore from the Earth's crust, combine it with carbon in a blast furnace, and we iron out plus carbon dioxide. And of course, we've got this iron metal. So we use the iron metal, but we can get back to iron oxide relatively easy. It just rusts, right? You get a bit of water and oxygen, and you get back to iron oxide quite simply. Of course, you need to put quite a bit of energy in here in order to get to that iron metal, but actually getting it back is not too problematic. So the useful embodied energy in some of our materials is difficult to extract, but what about composites? And this is the critical point I feel about composites is actually it's the embodied energy that's difficult to extract from, although you've got quite a large amount of embodied energy. So if you take oil and you polymerize a fraction of that into make polyacrylonitrile, which then you can then oxidize and graphitize to make carbon fiber, which then you mold into a composite material, and you get a carbon fiber composite. And actually, you're really far away from equilibrium here. You've got a very high exergy, what we call a high exergy value. And you've embodied a huge amount of energy into this system here. But what we'd like to do is get all the way back down to here, back down to the oil again. Okay, we'd like to get back down to this use. It's a very useful substance oil. But actually getting here is quite difficult. Now we can obviously recycle and reuse carbon fibers, composites. We can even extract out the carbon fibers from the system. But actually getting back down to this base material here, this liquid oil, is relatively difficult. And I think this is one of the critical things with composites is we're very good at embodying energy into the system, but actually we're not actually good at extracting out that useful energy. Now, another challenge, of course, with any of this, in any sustainability space, is the media. And we're being told, don't use plastic bags, don't fly in planes. Well, fortunately, at the moment, we're restricted from doing that anyway. Don't use the car to go to the supermarket. And of course, the newspapers. Sorry, I did pick one particular newspaper out here, but it wasn't by design. But these front pages really sort of tell a different picture that perhaps isn't quite the truth. And what we really need to do is be able to make some informed decisions about what's useful, what's not in terms of sustainability. So the challenge is actually making informed choices. And I just put one example up here of an informed choice. So if we were to think about plastic bags, say we went on a weekly shop, we might use something like 13 plastic carrier bags, approximately 100 grams of weight. And then if the shopping in the bag is 2/3 of which is plastic bottles and containers with about a kilogram. So the plastic bags are a small proportion of that weight. But what about the contribution of that to climate change? Well, in terms of total plastic in the UK, carrier bags only account for 1%, and plastic accounts for 1% of the UK's total carbon dioxide emissions. So if we stop using them, we reduce our emissions by less than 0.01%. So that's equivalent to avoiding driving 4 miles a year or turning off one light bulb for one day once a year. Now, of course, there are other implications of using plastic, particularly persistent plastics, I know. But in terms of its contribution to climate change, it's relatively minuscule. And so the data from this came from a good book, which is worth reading, Sustainable Materials with Both Eyes Open. What are other informed choices? Well, food systems, they contribute 21 to 37% of global greenhouse gases. And they're very significant contributors to deforestation, biodiversity loss, and declining water tables. And actually, the Amazon forest fires that we saw just recently are related one way or another to food production. The biggest problem, livestock, they use 1/3 of global cropland and they produce 15% of global gas emissions. So for every £4, this was in a New Yorker article, for every £4 of beef you eat, it contributes as much to global warming as flying from New York to London. And the average American eats that much each month. So you have to get things in context really about in terms of the climate. But what are the real challenges? So what about composites? Well, if we look at industries and the big emitters in industry, this is global gas emissions. It's about 44 gigatons of carbon dioxide equivalents. And deforestation accounts for 36%. And then you've got the energy processes giving 64%. Within that, the energy processes, these are the different emitters: buildings, industry, so it's a general industry there, transport and other. And then within the industry, you've got some very big emitters: steel, cement, producing a huge amount. Plastic only accounts for about 4%, so it's relatively low. What about carbon fibers? So about 20 tons of carbon dioxide emitted to produce 1 ton of carbon fiber. And if we consider the global production of carbon fiber supplied in 2015, it's just under 100,000 tons. And demand's going to go up to about this by 2020. So the global carbon dioxide emissions about 33 billion tons. So actually, in terms of carbon, okay, this is 1.8 million tons of CO2. So actually, the carbon emissions from carbon fiber production is about 0.005% of the carbon dioxide emissions. So it's relatively low. So we have to do calculations like this if we're going to really start thinking about this in relative terms, in terms of what's actually going on in the world. But as I said before, the embodied energy in carbon composites is quite large relatively to other materials, and this is carbon fiber here with a huge embodied energy, and being able to extract that is the key. So actually the challenge is really, the big challenge is extracting that embodied energy. But of course there are benefits to using carbon in the life cycle, carbon fibers. If you take the weight of an average family sized car and you calculate, you can do this calculation, we'll have these presentations online. You can work out how much fuel you can save by going to a carbon fiber. And you actually work out it's about a 26% increase in fuel efficiency by going to a carbon fiber system. But this is perhaps a bit of an extreme example. You do that, this is an all carbon fiber car. I've actually seen it coming off the production and it's a £2.9 million car. So actually carbon fibers in an average family saloon perhaps are a little bit on the expensive side at the moment. But there's also the challenge of end of life, and of course we don't want to see this sort of thing with planes ending up in the desert. We'd like to be able to reuse some of the material. But a very good example where we do actually reuse material are cars, but this is the current system for cars. So the big challenge for composites is actually that metallic systems are much more recyclable than composites. In fact, at the moment in the UK, and this is official figures, about 95% of cars, or 95% of the car is recycled in the UK. So how do we compete with that? This is a big challenge for us as an industry in being able to compete. And so we have to make choices. We need to make informed choices about what materials are best both for the application but also for the planet. And we need better information, and we need to have that presented in a way that can be understood for the application. Now, there's reasonable minds and emotional minds, but emotional minds do play a role. They're very important actually in decision making, and actually the way the world will go will depend very much on people's emotions and emotive responses to materials. And really, sustainability sits in the middle, if you like, between society, economy, and the environment. That intersection there. And we have to think about all of these considerations. But there is a big challenge in public perception. I took this picture on my bike as I was riding through Bristol last year when we had the climate change protests. And this is the big pink boat here on the bridge. We also had the Blue Planet, which has been very influential in terms of sustainability, and people protesting against the use of plastic bags. These are going to be big issues in the future. As climate change takes hold, public perception is going to grow and grow. So we need to shift. The challenge really is to shift our choices. We need more direct energy sources, fewer steps away from higher oxygen, away from equilibrium, if we're going to be able to extract some of that embodied energy. And we need some closed loops in the system to recycle and reuse. We can't go on the way we've been going. I haven't mentioned this yet, but actually reduce. We can't consume at the same rate that we've always done. And our choices need to be influenced somehow by some system that has, if you like, best worst scaling, to look at the best way to make a choice. You know, maybe, bad, good. These things need to be sorted out. But actually, one of the big challenges as climate change comes in is people and how this is going to affect people, and not just people, but their ways of life. And Brundtland, as some of you will know, gave a very good statement on sustainability, but it's perhaps a little simplistic. He said, sustainable development is development that meets the needs of the present without compromising the needs of future generations to meet their own. But what we're finding as climate change is becoming more and more present for people around the world, that actually it's just highlighting some of those big disparities in the world that were there. And they've been profoundly shaped by empire, the differentials of power between nations. If you look in the UN Security Council, the countries that have the most power are the largest emitters. And these differentials of power are greater today than they've ever been. And they're actually very closely related to carbon emissions. So actually the distribution of power in the world lies at the core of climate crisis. So it's actually not the global north who's going to suffer mostly from climate change. It's places like the Solomon Islands. We've seen flooding in India. And if we think about it, sustainability is not a Western or a global north invention. Many indigenous people have been working and battling, if you like, against their climate for many, many thousands of years. Aboriginal people in Australia have a very strong sense of climate. It's written into the language. And I think we have to incorporate concepts of other cultures if we want to collectively solve issues on sustainability. There are some good texts on this, on sustainability concepts, and what we call cultural capital. So we have to think about cultural capital, people being able to preserve their ways of life as well, and natural capital in sustainability. So without further ado, I'm going to finish there and unshare my screen and come back. Take any questions. Okay, so does anybody have any questions?
Yeah, great job, Steve.
Does any participants want to ask any questions? If not, we can go on to the next speaker. Oh, what about single-use plastic? Yeah, big problem. But I think the next speaker might actually answer that better than I can. But no, you're absolutely right. Single-use plastic's a big problem. But that's a habit we've got into. And I think, you know, it's something that it's a habit we need to break or have broken for us. Because I think we've got used to disposing of plastic as if it would go cascade down that exergy routes, you know, back down into what might be useful. And I think really we're not very aware about how these things persist. But actually, there's a huge amount of embodied energy that's buried in landfill. So there's a possibility to go and extract that embodied energy in the future. So there is actually a big resource of it out there. It's just what we do with it in the future that matters. But I was watching a program the other night about coastal erosion, and there's some landfill sites that are right on the coast, and so plastic is being exposed to in coastal regions, right into the environment. So anyway, I hope that answers your question, Anna. Any more questions? If not, we will go on to the next speaker. So I'd like to introduce our first guest speaker for the conference, Professor Tony Ryan from the University of... Oh, there are some questions. Sorry, Hayley.
No, Steve.
They're coming through very slowly. Here we go. What are the prospects and opportunities for natural fiber composites and bioplastic in the future? Well, I think there's huge opportunities for both of those things. The only issues with bioplastics is they're not as good as the plastics we've got already. They don't perform as well. There are possibilities, and the next question is it possible to compete or replace synthetic fiber composites? It is in certain circumstances, yes, it is. But again, you need performance in life as well. So I think there's a lot more work to be done in terms of improving the performance of natural fiber composites to compete with things like glass fiber composites and so on. What is the difference in terms of energy between thermosets and thermoplastic composites? Oh, I don't know the answer to that off the top of my head. I'm sorry. Another question. Have we considered recycling all plastics and reprocess it through additive manufacturing? Okay. I don't know if we have considered that actually. But I think, you know, an additive manufacturing at the moment does actually require quite specific polymers to do it. So, but yeah, I think opening up waste streams into things like that might be useful. Any more? If not, we better get on to the next speaker. We do have a Q&A session at the end, so we can ask questions then. Unfortunately, Professor Ryan's not able to be with us for that session, but we can always pass questions on to him and see if we can get an answer on subsequent days if you're present. So without further ado, I'm going to introduce our next speaker, Professor Tony Ryan from the University of Sheffield and the Grantham Institute. Tony studied polymer science at the University of Manchester and then did his PhD there as well. And then he went over to the University of Sheffield. He's a former PVC for Science at the University of Sheffield, and he's now director of the Grantham Institute, which looks specifically at sustainability. And Tony has been given many awards, including an OBE for his services to science. And he's going to talk to us about what's so great about fossils and could we make new ones? Over to you, Tony.
Thanks, Steve. So as you heard, my name's Tony Ryan. I'm a physical chemistry professor at the University of Sheffield and director of the Grantham Centre for Sustainable Futures. I'm going to turn my video off, so hopefully you won't get the sound coming in and out. So what's so great about fossils and could we make new ones? And I'm going to come back to themes that that Steve had highlighted throughout. So we're actually in the second century of plastics. In 1920, organic chemists admitted that plastics existed following a great article by Hermann Staudinger, and biopolymers got us started on plastics, natural rubber, for example, but then we fell in love with plastic from fossils, polyethylene, polypropylene, PVC, polystyrene, PET, nylon, PU, the thermosets that the composites community knows and loves, especially epoxies and other resins, but now clearly we hate them. I'll tell you why I don't think biopolymers and compostables are today's answer to replacing all those plastics, and ask the question, could we make neofossils, new fossils in the future to get around that embedded energy and, more importantly, embedded carbon dioxide problem by making non-degradable bioplastics from agricultural waste? And if we could do that, then we'd capture carbon from the atmosphere. And if the plastic or the composite was not degradable, then we could securely bury it and sequester carbon dioxide. So I've been a chemist, a polymer chemist for 40 years now, and it's really not a popular thing to tell people if you're out and about at a dinner party, not that I've been to any for the last 3 months. And so David Attenborough actually did me a big favor when I came back from being Pro Vice Chancellor to be a researcher again, because he got people interested in plastic. And again, you know, just like Steve, I pick my journals to ridicule carefully. So this photograph is from the Mail Online, and it shows a surfer on a beach. And I chose it specifically for today because it contains composites. So the surfer's on the beach and is looking in disgust at the piles of trash that have been washed on shore because the prevailing wind comes in on this beach. And you can see many, many plastic articles. The surfer's clearly disgusted by this because she's a member of Surfers Against Sewage.
Tony, we can't see your screen, unfortunately.
At all?
No.
Okay, so I'm sharing my screen.
I'm sorry about this.
It's all right, it's okay. Can you see my screen now?
No. Oh yes, here we go.
Now?
No, it's coming through. Yes, you better start again.
No, I don't need to start again because you've heard it all. And
yeah,
the slides, you know, you've heard everything that's on the slides, and you've seen a picture of David Attenborough, and you know plastics are hated, and this surfer's hating plastic. But let's look a bit closer at the surfer. She's clearly wearing plastic. That t-shirt's quick drying, either nylon or polyester. The pants she's got on, they're made from thermoplastic elastomer. They're made from lycra plastic. And that surfboard, what's the surfboard? Well, it's most likely a fiber reinforced polyester resin with a polyurethane foam core board. And let's not forget that carefully coiffured hair most likely has quite a bit of product in it too. And this is the issue for us around polymeric materials in general. We need to work out what we want to keep and what we want to change the way we use. So I had a conversation with a TV producer just the other day about the program War on Plastic. And it was quite intriguing because everyone clearly loves plastic now, because single-use plastic has pretty much protected everyone who's been involved in the work to protect the whole of society against COVID-19. So face shield, face masks, our composite masks, gowns, gloves, all made of plastic. And you can't get away from it. And you all need to love it. Someone asked a question about single-use plastic, and it's a real and present problem. And the reason is twofold. One's the exergy that Steve talked about, in that you don't get everything back. There are losses both in energy and also in material. And it's also, for packaging in particular, it's cheaper and less energy intensive to make a new product every time from virgin polymer. And the business models that we have of consumer disposal shifts the costs of dealing with that plastic away from both the producer, the retailer, and the consumer. Consequently, there's 8 billion tons in the Earth system, and 40 billion tons projected by 2050. And every year, about 10 million tons of that gets into the ocean, mainly because the majority of people live within 50 kilometers of the ocean. There's litter, but there's also a loading landfills. And in many countries, there isn't a working waste disposal system to deal with that plastic. So there's 3 billion tons of plastic on the Earth's surface, and there's 5 billion tons waiting to escape from poorly managed landfill. So some interesting stats. So annual plastic production equals the mass of all the people alive today. So we currently produce about 350 million tons of plastic, and there's about 400 million tons of people. But we only use 5% of oil and gas to make that plastic. And composites might be 5% of plastics production. So it's not really a big deal in terms of oil and gas usage. And what we absolutely have to do is stop burning it. It's just a shame that most of the composites applications are actually in areas where there are associated emissions with use. What does 8 billion tons of plastic look like? Well, it's a cube. It's a 2 by 2 by 2 cube. 8 cubic kilometers of plastic. If it was cling film at 13.2 microns thick, it'd go to Pluto and back 140 times if it was on a standard roll. And we could use it to wrap up the surface of the Earth, 510 million square kilometers, with about 25% to spare. And that's kind of the problem, that generally plastic is well dispersed and well distributed and small and thin and has high surface area. And when I was preparing to talk about this subject, I discovered another really, really scary thing. In the last 50 years, we've produced more plastic than all the people that have ever lived. 107 people at 62 kilos each is less than all the plastic that's been made in 50 years. 150,000 years of people production versus 50 years of plastics production. And reading that statistic a bit more, 7% of the people who've ever lived are alive today. And that's also scary. So, a newspaper I do know and love, The Guardian, had this headline: 1 million bottles a minute, the world's plastics binge as dangerous as climate change. Bullshit. This is a convenient truth. 5% of oil and gas is turned into plastic. 87% is burned, making carbon dioxide and causing global warming. That burning produces particulates and they cause respiratory diseases. They're the things we need to be cutting back on. And the inconvenient truth of global warming is in this slide. I produced it for an undergraduate lecture course using data from Mauna Loa, from Scripps, and it records the parts per million carbon dioxide in the atmosphere from the from the 1960s, about when I was born, when there was 320 ppm of carbon dioxide, up to today when there's more than 420. There's been a little downward blip because of 3 months of economic slowdown with COVID. And the blue line is a linear growth. It's not only the first derivative of carbon dioxide levels that are positive, it's also the second derivative. We're accelerating our production of carbon dioxide in the atmosphere. So when I was born, there was 320 ppm. When my PhD students were born, there was 360 ppm. And now there's 420. But we all signed up to the IPCC Paris Climate Agreement. And the Paris Climate Agreement says that to limit the global temperature to 1.5 degrees, we need to get negative emissions. And there's all sorts of fairy stories around how we might do that, but none of them are borne out by what we see, that actually we're still growing carbon emissions and look like we will continue to grow carbon emissions, even though renewable energy resources are coming on stream. What they're doing is they're essentially funding the growth. They're not taking out emissions. So we absolutely need to do some things to get to negative emissions. And one of the ideas that's around is heavily promoted by the Ellen MacArthur Foundation of the plastic circular economy. So to use renewable energy, to use renewable virgin feedstocks to make plastics that are designed and produced. They have a usage phase where they can be reused, and reusing plastics a really, really smart thing, or they can be recycled, where the recycled with added value. And then out of some of the use, there's anaerobic digestion and or composting. So create an effective economy for reusing plastic, reduce the leakage of plastics into the earth system, and decouple plastics from fossil feedstocks. And this looks very attractive to the emotional. Well, what about compostables? What do they do? Well, the Plastics Research Infrastructure Fund funded 8 UK universities to do some single-use plastic R&D, and actually they ran a big composting experiment out of UCL. And basically, I don't know whether you have a compost bin at home, but if you put compostable plastics in it, well, they don't compost. They don't break down. And if it says compostable on it, it'll most likely have in the fine print industrial composter. And if they do compost, well, what do they compost back to? Well, if it's anaerobic digestion, then you'll get some methane. But if it's in your compost heap, they're going back to water and carbon dioxide, which is immediately re-emitted. It's not even as good as using waste to energy systems, where at least when you burn the plastic, you recover some of the energy as heat. But people really want to do the right thing. And that's why greenwash cynical marketing works. So this is my favorite brand of water. It's kind of a quadruple con. Purified water, it's tap water. So it's in a bottle that has printed on it a plant bottle. It also has printed on it that it's 100% recyclable. Of course it's 100% recyclable. It's PET. You might think that actually people would be far better off drinking tap water from the tap. But, you know, I've kind of become a middle-class guy after all these years. And my favorite mineral water is Badwa. So Badwa actually does come from underground. It comes from the Alps. I live in Sheffield. You can get mineral water from Buxton. So what we did was we got the supply chain management master students to do an embedded energy calculation. It wasn't a full life cycle analysis on these two. And it turns out that the Buxton water is worse for the environment if you drink it in Sheffield than the Badwa that came all the way from the French-Italian border. Why? Well, the Buxton water in Sheffield comes in bottles that were made in Buxton. And the Buxton water, the Badwa water in Sheffield comes in bottles that were made in France. And Buxton's electricity has a very, very high carbon footprint, whereas France's electricity is 80% nuclear and has 20% of the carbon emissions of British electricity. And the majority of the carbon emissions in a bottle of water are actually blowing the bottle, not transporting the water. So if you do life cycle analyses, you uncover some interesting things. So what about bioplastics and degradable plastics then? So, PET, low density polyethylene, polystyrene, fossil-based and non-degradable, compared to bio-PET, bio-based and non-degradable. A polyester, polybutylene adipate or polybutylene adipate terephthalate, fossil-based and degradable, and polylactic acid. We've done the carbon emissions LCA calculations on those. So PET versus bio-PET. And if there's someone here from Coca-Cola, I apologize, it's just you have most pictures of plant bottles out there. If you read the label, up to 30% made from plants, 100% recyclable bottle. 30% from plants, that's the ethylene glycol, part of polyethylene terephthalate. 100% recyclable, it's polyethylene terephthalate. So this team from the University of Minnesota have done a really, really deep LCA on this, published in the Journal of Cleaner Production. And I'm just going to show you the highlights of it. So you make PET by reacting terephthalic acid and ethylene glycol. And so the post-fossil, sorry, the post-petrochemical processes are the same. So the polymerization to make PET, turning it into bottle-grade PET and blowing a bottle. So you start from paraxylene, which comes out of the petrochemicals plant, and you start from ethylene, which comes out of the petrochemicals plant. If you want to make ethylene glycol, you take ethylene, you make ethylene oxide, and then ethylene glycol. If you want to make ethylene glycol from biomass, you take biomass, you ferment it to make ethanol, and you dehydrate. So there's a burden to get to the first step of the process, polyethylene. If you want to make terephthalic acid from biomass, first you ferment to make isobutanol. Then that isobutanol is transformed into paraxylene, and then you go through the terephthalic acid process. And each of those processes to make the bio-based chemical has an extra energy input. And there's extra processes to get from biomass to paraxylene and to ethylene. And they're currently done at a very high carbon intensity by burning fossil fuels to do it. So, loads of graphs. Laser pointer, there we go. So, fossil-based terephthalic acid, wood-based terephthalic acid, corn stover-based terephthalic acid. These are, the wood is waste wood from the forest industry, branches, leaves, etc. Corn stover is what's left when you've harvested the corn. And then the colored bars are fossil ethylene glycol from corn, food, ethylene glycol from switchgrass, a fast-growing biomaterials crop, and ethylene glycol from wheat straw, again, another agricultural waste. And if we just look at the climate change bar, kilograms of carbon dioxide per equivalent, well, fossil PET beats all the other PETs unless you take into account the avoided emissions. So either the not burning the wood, not burning the straw, not ploughing in the corn stover. And in terms of, say, smog production, ozone, fossil wins all over. Particulates, well, you avoid a lot of particulates if you don't burn the agricultural waste. But acidification, fossil wins. Eutrophication, fossil wins. It's only really fossil resource depletion that fossil PET doesn't win. And on a whole load of indicators, bio-PET is worse than fossil PET and needs the avoided impacts to get anywhere close. So where would you take advantage of avoided impacts? Well, they become to be an advantage if you don't have to put so much fossil-based energy into the system. So should we burn more oil to make bioplastics? Clearly not. About 5% of oil and gas, 300 million tons a year, goes into making plastic. Can we make polymers from renewable resources? Well, yes, we can. Should we? Well, it depends on the life cycle analysis. And we should really only do it if we have a decarbonized energy system. Then we could sequester carbon dioxide from the atmosphere. So every chemical feedstock for the plastics industry can be made from biofuel feedstocks. And you can even make polyethylene from ethanol that derives from agricultural waste. So you can convert agricultural waste into ethanol, ethanol into ethylene, ethylene into polyethylene, and then you can't tell the difference. And every biopolymer has a crossover with its fossil equivalent as the grid carbon intensity falls. So as we get more and more renewables coming online, the emissions intensity, the grams of carbon dioxide per kilowatt hour of energy used in the economy, is falling and falling and falling. So we can then calculate the amount of carbon dioxide per kilogram of polymer that we make over time as the grid carbon dioxide intensity falls, and include the avoided emissions in those calculations. And then you get a benefit from making biopolymer. And the benefit you get depends on what the inputs to that polymer are, whether how much is in the form of electricity, how much is in the form of process heat, and how much is actually embedded in the resource, feedstock resource. So the government has an electricity defossilization forecast based on the rate at which we're employing renewables. So that falls off over time, and it doesn't fall off quickly enough to be able to show you well. So I'm going to double it. I'm going to say we're going to do twice as well as the government thinks we're going to do. So now for bio-PET, polylactic acid, fossil polystyrene, fossil polyethylene, and fossil PET, we see the carbon intensity of those polymers fall as time goes on. And often, if you go into like a tree-hugging eco-cafe, they'll have compostable PLA for their cups and plates and knives and forks that are replacing polystyrene. And actually, that starts to make sense in about 2031 to replace polystyrene with PLA. If we double the rate at which we decarbonize the electricity system and we decarbonize the heat system at the same rate, then that fall off happens in 2025. So it makes sense to replace polystyrene with PLA. But it doesn't matter how fast you defossilize the heat system and the electricity system, bio-PET is never better than fossil PET. And to answer those questions about composite materials and composite resins, then they're most likely to be more like PET than they are like a polystyrene or polyethylene. So how much plastic's produced? 300 million tons a year, 0.3 of a gigaton. How much agricultural waste? 20 gigatons a year. So if we use defossilized energy to make non-degradable plastic or non-degradable composites from agricultural waste, how much carbon dioxide could we sequester? Well, about a gigaton of carbon dioxide per year, every year. And why is burying plastic better than burying carbon dioxide? So BECCS is kind of the holy grail, bioenergy with carbon capture and storage. And it kind of makes sense to everyone. It's a lot easier to store plastic than it is to store carbon dioxide because you're burying a solid rather than burying a gas. So what does a neofossil have to do? So it needs to lock up carbon and safely go down a hole, not degrade back into carbon dioxide and water, so PLA's out. PET might work if we can prevent those new enzymes that have been discovered that can eat it, and thermoset composites look a great idea to bury. If we can make biopolyethylene, then we'll really be onto a winner, and we're doing the LCA on that now. And actually, I have a couple of PhD students working on thermoplastic composites based on polyethylene, so I should be able to update you a bit later. So for the second century of plastics, what should we do? Well, we should make sure we're not distracted by the convenient truth of all that plastics waste and all that composites waste. We should understand the benefits of plastics we want to maintain in a circular economy for now and balance them against health and environmental costs. But more importantly, we need to work out when we can use polymer materials to sequester carbon dioxide and then stop being a circular plastics economy and start being a linear plastics economy again. But in the second linear plastics economy, using it to take carbon dioxide out of the atmosphere because you're using this year's photosynthate. So my message to you is make fossils from composites and not composites from fossils. Thank you very much.
Thank you, Tony. Thank you very much. So we now have some questions. I'm just going to go through them. Find where we started actually on the question list, because I think we've got quite a few questions here.
Yeah, there's a shock.
So bio-based versus synthetic. This is a question from John Summerscales. To what extent is LCA influenced by developing small-scale processes versus established scaled-up process, respectively?
Well, if you do the LCA, you'll be able to tell the difference between a small-scale process and a large-scale process because it'll come out of the LCA. Because basically you do carbon accounting. So, you know, that question will be answered by making the right life cycle analysis. And I was, you know, interested to see that your next speaker is actually an LCA speaker.
Yeah, well, he does LCA for a living, yeah.
Well, no, and I think, you know, if you're going to ask a question in this arena, then the answer is do the LCA.
Yeah.
Because it provides the evidence for decision making.
Yeah. The question from Stella Job, Tony, your data compares the impact of bio-based with fossil-based on the basis of global warming impact.
Yeah.
What about aquatic toxicity and other effects?
Well, okay. So if you that is a real issue. I don't know how, and it's not really well researched. If you make PET from bio-based and from fossil-based materials, when it goes into the environment as microplastic, you know, as fibers shed from a fleece, then it's PET, and it doesn't matter what its source was. Okay, if you make a fleece out of PLA, then you'll have holes in the armpit really early in the life of the fleece, and you have to trade those two things off. So some, you know, you wouldn't really want it to be making garments out of things that were readily compostable. Yeah.
Thank you very much. I think we've only got time for 2 questions, unfortunately. But so
I'm going to try and come back for the Q&A because
okay.
I'm co-chairing the STFC meeting.
Okay. Oh, well, we'll look forward to seeing you then, hopefully.
Hopefully.
Well, thank you very much. And I'll move over now to our next speaker. So we have Professor Callum Hill from JCH Industrial Ecology Limited. Before that, Callum spent many years at Bangor University. And then he took up a chair at Napier University and has since moved back to the lovely Anglesey and is has been running his own company for many years, JCH Industrial Ecology. He does LCA for a living. You also, I think you still have a 20% visiting position, don't you, at a Norwegian university as well?
Yes, that's right, yeah.
Yeah.
Near Oslo.
Yeah, so Callum's going to talk to us about meeting the need for product-specific LCAs for composites, and this is lessons learned from the Dhakamat project, which was an EU-funded project, I believe.
Yes, that's right. It's still going. We've got another 2 years to run on it, so
okay.
I haven't got all the answers yet.
Over to you then, Callum. And if you want to screen,
yeah, I'm sharing my screen now. So let me know if you can see it, so that we don't have a blank screen. Are you seeing it?
Yes, we can see that. If you just click F.
Yep.
Or,
There you go.
there we
Okay,
go.
good to go. What I'll do, actually, I can't turn my video off now. If I'm clipping, could you let me know if the sound clips, and then I'll turn my video off.
Yeah, I'll let you know if anything goes wrong.
Okay, so yeah, I thought I'd talk about a real life problem because I do LCA for a living, and that does involve trying to measure things in real life rather than what theoretical answers we might get from doing LCA. And it's a messy business, quite honestly. You don't always get nice, simple answers from doing LCA, which is unfortunate. So this is the Dhakamat project. The Dhakamat project is formed of a consortium of partners who have different functions. Some people, some companies are making wind turbine blades, some are doing fundamental research into composites, and JCH at the bottom there, we're doing the life cycle assessment. The whole point of doing this project is to make composites which are damage tolerant and therefore have longer lives. Now, in making these composites, we might end up making something that has a higher environmental footprint at the beginning of the life. But if we extend that life, then we would hope, because we will need less of it overall, or we'll need less interventions, less repairs, ultimately fewer replacements. The idea would be that we would recover that environmental impact from the beginning through the whole life cycle. So it's important not just to measure the beginning, but to measure the whole life cycle. And that includes the end of life, of course. And I'm always quite amused from the project proposal that they showed a picture of a piece of wood as a perfect damage tolerant composite, because I've spent about a quarter of a century of my life working on timber. And it's nice to see that we're trying to emulate nature when we're creating these composites for the future. So we're responsible for a work package within this project, and we have to do life cycle assessment, the LCA, and also something called life cycle cost assessment, LCCA. Very similar process. We have to understand what goes into the composite in the first place, how we manufacture it, but then we have to understand other parts of the life cycle, such as are we going to repair it, are we going to replace it, and ultimately how are we going to dispose of this. And all these interventions have burdens associated with them. They have financial costs and they have environmental burdens, and that's what we're concerned with measuring. So looking at the situation for the composite that we're looking at for this project, this particular example is for a wind turbine blade, but we're also looking at bridges, but I thought I'd just talk about wind turbine blades today. We're going to have a number of components that go into this composite. This will include vinyl ester resin, glass fiber, maybe a carbon fiber, sizing agent, gel coat, fillers, and various other components. So we have to understand the environmental impacts of each of those components that go into the composite. So the first thing we had to try and understand was, what are the impacts of these different ingredients? And that was one of the first issues that we encountered. When I say we, it's me and my colleague, Andrew Norton, who's also working on this project. There's not actually a lot of information out there. It's a very, very secretive industry. So this is what we gathered. I'll expand this plot in a minute. And the first thing that comes out of it, Steve actually showed some numbers for carbon fiber. Carbon fiber has a very, very high burden compared with glass fiber. So if we were going to make choices just on that basis, we would choose carbon second over glass because it has a higher burden, but there may be other issues that we want to take into consideration, such as the performance of the composite through the life. And I'd like to just take a moment with this graph to explain what we're showing here. On the left, you'll see something called EE in megajoules per kilogram, and this is something called embodied energy. And I've heard embodied energy mentioned, and I've also heard embedded energy mentioned, and there's a lot of confusion as to what these terms mean. It's unfortunate that embodied and embedded sound very similar, but they're not the same thing. So an embodied energy is the energy that has gone into manufacturing, transporting, extracting the components. So it's not a form of energy that you'll ever get back. You'll never recover the embodied energy, but the embodied energy can be used as a measure, as some sort of proxy for the overall environmental burden. So here we have a plot of embodied energy against global warming potential. And that has a reasonably good relationship, linear relationship between the two. And one of the things we're trying to do with the research here is to try and understand if we get these sorts of relationships with other environmental burdens as well. We've had some aquatic ecotoxicity mentioned as another potential measure of how much of an environmental burden a process or a product is. The problem with a great many of these burdens that you get in LCA is that the science isn't fully understood. We have to understand the chains of cause and effect through the environment. We don't always understand the science as well as we do with things like global warming potential or ozone layer depletion. And that's one of the reasons I'm particularly interested in embodied energy, because maybe we can use that as a proxy for determining what the environmental burden is. So just to zoom in on part of this graph, so we're now looking much more closely at the region that we're interested in from the point of view of the project. And what we're comparing here is if you look at the coloured triangles in the circle, we're looking at the resins there, because one of the main things we're doing is altering the composition of the resin to see if that alters the fracture toughness of the composite, to see how it affects crack growth, crack development during the lifetime of a wind turbine blade. Because during inspections, one of the things they'll be looking for is cracks, and if a crack gets to a certain length, they have to replace the blade. Otherwise, there's a catastrophic failure, which means that perhaps the whole turbine gets damaged and they have to replace it. So the idea is obviously you get in with maintenance, replace a blade before that catastrophic failure happens. And that's one of the things I'll talk about a bit later on in the talk. So one of the things we were interested in was looking at the impact of an unsaturated polyester resin versus a vinyl ester versus an epoxy, which I haven't shown here. The vinyl ester is the resin of interest from the point of view of external applications, because a vinyl ester, if we look at the structure of these resins, is much more tolerant to moisture than an unsaturated polyester. So I've just shown on the unsaturated polyester there these ester linkages, which is where the name comes from. These are very vulnerable to attack by water. If you look at the vinyl ester, you don't see these apart from at the terminal parts of the chain. So this is the kind of backbone of the chain. And then we have to cross-link that to make a thermoset resin, which is a rigid resin. You can't melt it and form it after it's gone through its curing process. And generally for that, we will use cross-links, which are either made of styrene or methacrylic acid, or a mixture of styrene and methacrylic acid. So as part of the LCA that we were performing in the project, we had to understand what the formulation of the resin was, and also look at what the environmental burdens of the ingredients of that resin were. So one of the issues is to understand how the new vinyl ester resin that's going to be created for the project is compared with the state of the art. And a diagram very similar to this was shown in a previous talk. It's not something I expect you to kind of absorb in one go, but it just shows the kind of considerations that have to be included in a life cycle assessment. What we're basically doing is extracting ingredients, feedstocks from nature, and then we process those feedstocks. So as we pass down a chain to producing, if you look at the bottom left-hand corner, the epoxy resin, which is part of the ingredient of the vinyl ester resin, we have to go through all these intermediates. Now, I've extracted these numbers from the internet, from Plastics Europe website. And as we pass down, and we're looking at the burdens per kilogram, these will increase. The more processing that you put into making something, obviously the higher will be the embodied energy, and also the higher will be the carbon footprint, which is measured in kilograms carbon dioxide equivalent per kilogram of material. There is a relationship between the two, as I showed in one of the earlier graphs. The relationship isn't exact, because the sorts of things that will affect the carbon footprint are things like grid decarbonisation, which Tony talked about previously. So we may not have an exact relationship, but nonetheless, we will have some sort of relationship between the embodied energy and the environmental burden of interest. And for this particular talk, I shall just be considering global warming potential, which is obviously extremely topical, but we can expect there to be a relationship between this embodied energy and other environmental burdens as well. And this is a similar sort of plot, but it shows some other ingredients which will go through to make other parts of the resin. So these are the kind of process chains that go into forming an LCA. Now, it would be not just extremely tedious, but it would make our lives almost impossible if we had to track everything back through to nature. So over time, what has happened is that databases have been built up, which we can rely upon. They're usually reasonably up to date. They get updated periodically, and they use quite often industry data. And that we can use by interrogating the database to get the compound of interest for our study. You'll see there's gaps here, and these gaps, sometimes they're real gaps that we don't have the data, and sometimes the data gaps exist because this information is considered to be quite commercially sensitive. And we have an issue when we do LCA that we can't always get the information we want. So to get around that, we have to either build models, or we have to use proxies. We have to use something that we think is representative, a close representative of the thing that we're actually trying to understand. As time goes on, as more LCAs get done, we will fill up these gaps. The databases will become more reliable. But it's important to understand that we do have data gaps and we do have uncertainty. So quite often you'll see an LCA that compares one thing with another, but it doesn't include the uncertainties. And the uncertainties can be actually quite crucial when we're trying to make these sorts of comparisons. So it's not an exact science. So if we go into a database like EcoInvent, which if you've got the money, you could purchase and you can get this information. We're trying to understand how a vinyl ester resin is made. And in this project, we're trying to understand how it's made, even when a commercial company considers the information too sensitive to actually tell us the ingredients. So the way we do this is that we split the process chain down to its ingredients, where we can find things that we do know what the answers are for. And I don't know how well you can see this slide, but if you go down the two green boxes, then there's three white boxes. Those three white boxes have got the ingredients that go to make our vinyl ester resin. And we know that these epoxy resin, methacrylic acid and styrene are the three components that are going to be varied to make the new resin. We don't actually know what that resin is yet because that's still part of the development process. But because we know what should be going into it, we can create a calculator which has the burdens of the epoxy resin, the methacrylic acid and the styrene, which are known quantities for us. And we can put that into a spreadsheet and hand that over to the company, and they can put their numbers in, which they consider to be highly sensitive, but they can then spit out an answer for us. So by producing a calculator of that type, we can produce a graph which basically shows, well, what happens if you vary the styrene? What happens if you vary the methacrylic acid? And what happens if you vary the epoxy? Now, within that region, within those lines, will lie the optimum resin formulation. Now, we may not be going for the one that has the lowest burden, which in this particular graph would be a 0.2 weight fraction epoxy. The 0.8 weight fraction will be composed 100% of styrene. That's a non-functional resin. That is a resin that simply wouldn't be any use. So we can superimpose on these sorts of graphs, graphs that show the functionality of the resin, how strong it is, how stiff it is, how tough it is. And there are plots that you can buy from Granta Design, I think it is, Ashby plots, which will actually superimpose that other information on top of the environmental information. So you can make a choice then. You can say, well, it's no good making the one with the least impact because that is a resin that simply won't function in real life. So we have to go into a region where we know we have the functionality we want. What's the lowest burden that we can get with that? But it isn't necessarily the choice that you make at the beginning, because that may affect its behavior during the whole life. It might be a very strong resin, but it might turn out that it's very brittle and you end up with lots of cracks. So it has a very short lifetime. So there's a lot of information that has to go into this. It isn't just what has the lowest environmental burden at the beginning. it's the whole of the life cycle, and that's what we're concerned with with this project. So when you make a resin, you have to have a cross-linking reaction, and you have to initiate that cross-linking reaction with these particular thermoset resins. And again, you have a choice of initiators. It could be any of these. It might be a combination of them. But the important thing is that if you look at the bottom of this slide, it says addition about 3 PHR, which is shorthand for parts per 100 resin. So we're looking at maybe a 3% addition, something like that, in terms of weight of the initiator. And that can be quite important, because you might look at an initiator and it might have a high burden. But if you're not using very much of it, you obviously multiply the weight of the initiator by the burden per kilogram, and you might find out actually it doesn't really matter very much. So we could spend a lot of time concentrating on getting very accurate numbers for initiators, only to find out that the initiator doesn't actually count very much towards the total burden of the resin. And that's one of the great uses of LCA, is to make choices during manufacturing processes. So you concentrate on what are called environmental hotspots. What does have an important impact? What is worth concentrating on? And Tony was talking about something like that earlier. What's the correct choice to make based on the information we have for the whole of the life cycle? So this is what we have. And if we look at some of those initiators, we find that actually we don't always have the entries that we want, but we might have something similar. So, for example, at the bottom, we have tertiary butyl peroxybenzoate, and in Eco-Event, there is no tertiary butyl peroxybenzoate, but we do have benzoic acid. So as a first go at this, we select things which we think are reasonably close chemically, which involve similar process chains. I've actually chosen cobalt for cobalt naphthenate, because I know that the actual cobalt metal will have a much higher impact than the initiator itself. And this is just for a first go. We're trying to find out if it's important. So if we're going to make a choice on this basis, we choose something that we think probably has a higher impact than the actual initiator. If we find out the initiator is important, then we will drill down, we'll get more detail. But this is just to see how important the initiator is in the whole of the LCA. We also add 2 composites, and this is a very important part of the composite from the point of view of damage tolerance, something called a sizing agent. And this is the thing that effectively bonds the fiber to the resin. The resin isn't necessarily going to bond very well to the glass fiber, so we have to have something in between, which is kind of an intermediate coupling agent. But if we look again, these are typically added at 0.5 to 0.6% by fiber weight. So the suspicion is already that there's not very much there. It probably doesn't matter. So again, as a first go, we look into the Eco-Event database and we see if there is something that represents the initiator. And actually there's something that's quite close to what these initiators are, which again, as usual, turn out to be great trade secrets. So we have to use something that we consider to be a reasonable proxy. In this case, it's something called TEOS, which is tetraethyl orthosilicate. So we can use that as a proxy. So then we create a composite, which is a virtual composite. It's a composite that is in our model, it's in our spreadsheet model. And we can do this before they start making the composite. Then we can offer this model as part of the decision process for when they start changing formulations. Okay, you're going to vary this amount of resin, you're going to use that initiator, you're going to use that coupling agent. What effect does that have on the overall impact of the composite? And this is what we found. We rather suspected that this is what we would find. The sizing agent and the initiator are of no consequence. They do have an impact, but it's a very small impact. And actually, if I was to put error bars on these plots, you'd find that the sizing agent initiator, they fall within the errors that we have within these kind of analyses anyway. So we can effectively ignore those. If they were then to choose something outside of that range that we've looked at, we might have to revisit it, but I would still be very surprised if they turned out to be of any importance. So it's the fiber and the resin. And in this particular case, we're looking at glass fiber. and we're looking at the vinyl ester resin, which we can vary. So that tells you the relative impacts. The only two things we need to worry about are the fibre and the resin when we're making a selection for the composite. And the only two things that we are then going to vary are the weight fraction of the fibre, and then obviously that will affect the weight fraction of the resin. So again, within these lines falls our composite. Now this goes to ridiculous limits. It goes from a 0 weight fraction glass fibre, which isn't a composite, of course, it's just the resin, and it goes to a 1 weight fraction, which isn't a composite because it's just the glass fibre. But this basically encompasses the extremes, and somewhere within those extremes will be the actual composite that we manufacture. It might have a weight fraction of glass fibre of about 0.6, for example. So then we could look at these lines are for our different vinyl ester resins. So again, we can look there and we can look at what the burdens are. When you start doing these sorts of analyses, you find that the burdens, the differences in the environmental burdens, in this case, the global warming potential, turn out to be quite insignificant compared with the whole of the lifetime. So we might find out that one single inspection of a wind turbine blade would have a greater burden in terms of the downtime of the wind turbine, the amount of energy that's gone into transporting whatever's needed to fix the wind turbine or to inspect the wind turbine. We might find that has a much higher burden than this actual choice in the variation of the resin. But again, this is what LCA is for, is to find out what's really important. So we haven't got there yet, but it's already telling us that actually the band's quite narrow when we vary the vinyl ester resin. So we are in one way a step ahead of what the project's doing, and that they haven't finished choosing the ultimate resin, but we have already done analysis that tells us it probably doesn't matter very much in terms of the whole life cycle. And this one is just using volume fraction rather than weight fraction, which is a more common way of representing composites. So these are the sorts of things we have to consider: the materials, any energy that goes into manufacturing, in our case a wind turbine blade. For curing, we might do it in an autoclave, so that has energy associated with it. Laying up the composite has energy associated with it. You've got to run the factory, that has energy associated with it. And then we have issues which are related to the service life of the blade. How long is it going to last? What sort of maintenance regime are we going to use? How many inspections is it going to have during its lifetime? The really important thing from the point of view of wind turbines in that case is the downtime. How much lost energy production because we've had to shut the blade down because of an inspection. And if we don't inspect regularly enough, do we have a catastrophic failure? That would be a much more serious amount of downtime, plus we'd have to probably replace the wind turbine blade. We also have to consider end of life. There is going to be quite an issue with wind turbine blades as they come to the end of their life, because we don't really know what to do with them at the moment. But they actually have a lot of functionality in them. And although people are concentrating on disassembling the blade, recovering the resin through maybe a pyrolysis process or some other process, they're actually quite useful for many, many other things. And I think that reusing them in a different function, maybe a bridge, a footbridge, or as roof trusses or something like that, could prove to be a much more useful end of life. So that's one of the things we'll be looking at. And then what we're doing is we're comparing our Dhakamat system, our damage tolerance system, with what's already out there, and trying to see and hopefully finding that the environmental burdens for this Dhakamat system are lower than the state of the art. The people that write these proposals don't always think about how much trouble they're causing for the poor LCA practitioner who has to do the work. Just saying, oh, we're going to have a 30% lower environmental footprint and 30% lower cost at the end of life compared with the state of the art is very easy to say. It's damn difficult to prove. We have to answer questions like, well, how big's the rotor? And the relationship between the rotor and the wind turbine output, because obviously the bigger the wind turbine, the more material goes in to make the rotor. So we have bigger power output, which is great from the point of view of energy in, energy out, the embodied energy in manufacturing the wind turbine. But we need to get more energy out of a wind turbine than we ever put into it. Otherwise, there's no point making it. We're quite safe on that part of it, but we're down into a much more accurate realm here, because we're changing the material composition of the rotor, and we're affecting its behavior in life. We have issues such as onshore, offshore. There's going to be much different factors involved in the inspections, different composition of the rotor, and the fact that the rotor may, in this project, have sensors embedded. And as soon as you start putting sensors in, you start including electronics, and then you've got a whole new set of LCA calculations to do. It can get very difficult. So here's just an example of, if you increase the output of the wind turbine blade, then the blade gets bigger, and as a consequence, the weight of that turbine blade goes up. But we're looking at weight per megawatt of output, so we actually see it go through a maximum and then starts to decrease again. So we've got this weight of material, which we're largely concerned with the resin and the fibre. At the end of life, obviously, that's going to have to be disposed of or reused in some way. So we've got that consideration. We've also got consideration of the environmental burdens per kilogram of resin and fibre that we also need to consider. We need to be thinking about downtime, time between inspections, what rules there are for the limit states. I mean, how long was the crack? Do we have to replace the blade? Now we've seen a crack, do we have to replace it immediately, or can we wait until the next inspection? Is it more important for a state-of-the-art blade, which is less damage tolerant? We hope it's more important for the old type of blade, less important for the Dhakamat blade, but we simply don't know that yet. When do we repair? When do we replace? And how far away is that wind turbine? These are all considerations that have to be put into our model. And we're only just starting on this process at the moment. So I'm hoping I'll be able to have some answers for the next conference for that. We basically have impacts associated with the maintenance effort, which go up if we have increased maintenance effort. So that might mean more inspections or more repairs, but we also have lower costs associated with more maintenance, because we have a lower probability of failure. And somewhere in between there lies the optimal strategy. And one of the things we're going to have to do is to find out where that optimum number is going to move. And that's pretty tricky stuff. So hopefully by next time I'll have more to say about that. This is what I say about people that write proposals, don't always think about the consequences of what the LCA practitioner has to deal with. So we're looking into this at the moment. More to say about that next time, hopefully. And here's an example of wind turbine blades as we get bigger. What happens to the output, the burden, the environmental burden in terms of carbon dioxide per kilowatt hour produced as the blade gets bigger, as the wind turbine gets bigger. And we can see we're starting to bottom out at around about 2 megawatt. There's even bigger wind turbines going in these days. So in terms of output per kilowatt hour, we again reach an optimum level in terms of what the impact is. So this is sort of related to an economy of scale issue. Obviously, as the blade gets bigger, if we turn the wind turbine off, then we're losing production. So we have to take that into consideration. And again, we see a relationship here between the greenhouse gas performance of the blade compared with the average wind speed. So this is a relationship that we also have to take account of. It's not just directly related, because it depends how fast the wind's blowing. If the wind's blowing faster, we get more energy, so the impact is lower. But if the wind blows faster, we can't necessarily go out there in a boat to fix the wind turbine blade. So if the wind turbine blade breaks or fails when the wind's blowing fast, then there's a higher loss of production than there would be maybe when we did an inspection when the wind speed was lower. So it's not that easy to get a straight answer. And finally, just a quick look at what the expected lifetime is. This is from a study of wind turbines that were located in Denmark. We're looking at around about 18 years, something like that, average, but we have a distribution. So we have to use some statistical analysis to, what we're trying to do is shift that normal distribution, which is not normal actually, if you look at it slightly skewed, but shift that to the right because we want more damage tolerant blades. We would expect longer lifetimes. If we get longer lifetimes, we would expect the burden per kilowatt hour to be reduced. So this is all stuff to do. And that is the end of my talk. And there you see a link to the Dhakamat project. The graphs and the plots that are on this talk you will find in various reports that you can download from the website. You're very welcome to visit, and thank you very much for your attention. A very strange experience talking to a blank screen. Thank you.
Thank you very much, Callum. Okay, we're going to move to the Q&A session now, but I think we'll do a few questions about your talk specifically first, Callum.
Okay. I haven't done anything with the share screen. Have you switched it off? So.
If you shared, you unshared your screen?
I can't even see where that is at the moment.
Unshared.
It is unshared. Is it?
It's unshared, is it?
Okay.
Okay. Excellent. So if the presenters could put their cameras on, and then we can, I think Tony runs back with us as well. That's great. So hello, Tony. So why are glass and carbon fibers so different in terms of embodied energy? Does the huge difference justify use of carbon fiber then?
Mm-hmm. It depends, like with most things, doesn't it? I mean, they're obviously lighter. So there may be applications through a whole life where, because a composite is much lighter, you use a lot less energy for the whole life. Maybe it's a vehicle that you're using for transportation or aircraft or something, in which case you use a lot less energy through its whole life. I think the answer about why it's got a higher burden is to do with the processing temperature.
Yeah.
Furnace.
Yeah. Does the price of glass and carbon fiber relate to their embodied energy, in your opinion?
That's a very good question. Yes, they do. I mean, there's been a lot of studies of this in economics of how embodied energy and price matches, and they do match, but the match isn't exact because it obviously depends on the price of energy and other complicated factors. But yeah, I mean, ultimately, there should be a relationship between embodied energy, environmental burdens, and price. We should be getting price into the environmental impacts. We're not very good at doing that in economics. That's something that's missing, something called externalities. But ultimately, we would expect to see that, yes, going forward in this brave new world that we'll be entering after lockdown.
There's an interesting development in the kind of field of social anthropology as well, where kind of history has been revisited in terms of energy history as opposed to human history. And you learn a whole load of interesting things about actually studying the embodied energy and the energy return as to why and how things happened. Something that historians have really historically not thought about.
Yeah. There's some very general questions here. So what about carbon fiber composites at the end?
Yeah.
End of life. Yeah.
Like what happens then? I guess both of you might want to say something about that.
So the question is, right, if it costs you 10 times as much energy to pyrolyze the monomer, pyrolyze the thermoset back to the monomer, and the best you can do by chemical recycling is to make something you could burn and then recover that energy. Yeah. And you get the fibers back, but now you don't know what fibers they are, you don't know where they're from, you don't know what loads they've been put on. You know, the recycling cost massively outweighs the benefit. And we should make those decisions, those cost-benefit decisions, rationally. And given the volume of composite, especially the high embodied energy composite. You know, why throw good energy after bad?
Yeah.
Would be my view. You know, you could pulverize it and use it as road filling. You know, you're only ever going to downcycle a composite. You're never really going to upcycle a composite. The volumes aren't very high and they're super stable. Yeah, you know where I'm heading now, don't you? Get them buried.
Get them in the ground.
Before we bury them, they quite often they have functionality.
Yeah, yeah.
Use. I mean, a wind turbine blade can't be used as a wind turbine blade once the cracks reach a certain length or it's reached a certain design lifetime, but it's well over engineered for making a footbridge or a roof truss.
Yeah, yeah.
Yeah.
You know, we need to get imagination into it.
Yeah.
Yeah. So I think something like, I mean, having an idea of a sort of I have a picture of a car that's sort of, you know, put together out of composite parts. And you can take those parts out then, so you have a compartmentalized set of composites that you can then use for other things.
The Lego car.
Basically.
Well, and I think, I mean, joking apart, Steve, this whole idea of designing for demanufacture, right? So you know, if you were smart about the way you designed an artifact, so that you could recover composite parts, you know, I mean, I know you were joking about Lego, but if you made things from spars,
I never joke about Lego, never.
And girders, then you could reuse them.
Yeah, yeah. I do a lot of work with the built environment, and this is an issue that we're really interested in: is deconstruction and reuse of the components, which are usually perfectly functional. It's just that we don't need the building in that shape or form anymore.
I think the problem with composites is we've obviously had to put a lot of effort into ensuring the interfaces are good so that they work. Yeah. But then the interfaces are too good for the end of life. The next you know, and that's another key area. I don't know if interfaces need to be reversible somehow.
Well, to switch them on and off.
It's a bit to get to that stage. You're probably over engineering it. And
well, so one opportunity might be to actually use the properties of the reinforcement, the fibers, to do some of that for you. Because if you use microwaves, right, carbon fibers heat up enormously in microwaves, whereas lots of resin doesn't. So you could actually use the carbon fiber to burn the resin off or destroy the interfaces without doing much damage to the carbon fiber, because you're just giving it a little 200 degree spank that doesn't affect it but does affect the matrix. Especially if you have thermoplastic composites. I mean, that'd absolutely be a way to do it.
Oh yeah. I've just got some questions here coming up as we're talking. So fossil plastic will be a problem for the future. What's the strategy to face that problem? So I guess it's to you, Tony. So the idea of putting it in the ground, but then are we just not putting the, I guess the question is, are we just not putting the problem off?
Well, no. So okay, and perhaps I didn't make a good enough job of kind of explaining my hypothesis. So basically, plastics are made, like you said, from buried sunshine. Okay, so current plastics that are made from oil and gas, right? That material was biomass millions of years ago. Okay, so if you make plastic from today's biomass, it's taken carbon dioxide out of the air this year. Okay, so then if if it was agricultural waste and was left lying on the ground, or it was burned, then you'd return that carbon dioxide to the atmosphere this year.
Yeah.
But if you turn it into plastic and curate the landfill, right, then and we use policy and legislation to reduce the number of plastics that you can use. So it's only legal to have, in large applications, polyethylene, polypropylene, PET. Then you could fill old mines or old landfills with stuff where you knew where it was, and if you wanted to dig it up later, you'd have a really, really good petrochemical feedstock.
Yeah.
But what you can't do is chuck it away, because there is no away, as you pointed out. So you have to curate the end of life if you're going to use plastic and composites to sequester carbon dioxide.
But there's also this myth, I mean, you mentioned it, this circular economy myth, that somehow things can go around forever. And what's very seldom shown in these diagrams is something called dissipation. You're inevitably going to lose a percentage. And depending on the lifetime of that product, it's quite astonishing how quickly things leak out the system. Which of course is what we're seeing with polymers, which are out in the environment, in the oceans. It's a very small amount leaking out, but it doesn't need to be a very big amount because the lifetimes of these things is very short.
Yeah, exactly. Question for Callum. I've just been told to ask questions that have got the most votes, and I was asking questions down the bottom of the sheet, but the question, I apologise for that. Well, we will get round to most people's questions, but since these have got the most votes, so it's a question for Callum. Have you identified particular sensitivities in LCA data for composites, e.g. specific resin, chemical precursors? This is a question from Stella Job.
Well, I mean, the data was shown earlier that some resins have higher impacts than others. And obviously the carbon fibre has a much higher impact than the glass fibre, but I'm not quite sure how to answer the question, to be quite honest with you, in terms of particular. I mean, you can follow these process chains through and see, I guess she's asking the question about, is there some feedstock that we could replace which would have a lower burden than what we're using already? I haven't personally identified any such replacement. I mean, as Tony was saying, quite often you make an assumption, oh, we'll go for a bio-based alternative. You find out it has a higher impact.
Yeah, and interestingly, we use the same software.
Yeah, you can.
Clearly.
Yeah.
Well,
I mean, it's got,
right. But the methodologies need to be harmonised in many ways, don't they?
quite honestly, the thing that concerns me more than anything at the moment is these blooming data gaps, which can be quite severe when you're trying to do LCA. You just haven't got the data you want. Very seldom will an LCA practitioner admit this. This is the dark hidden art of LCA. But sometimes we just don't know the answer.
I've got another popular question. This is for Tony. Hi, Tony. Really engaging talk. Thank you. If the UK were to fully remove coal long term, as we saw they did for 2 months recently, how would the emissions impact compare with France's electricity mix emissions, do you think?
Well, so France gets 80% of its electricity carbon free. So, you know, we haven't been using coal. You know, coal's not really going to start up to any great extent now. You know, once you decommission a coal power station, it's, you know, they're really hard to turn on and off, which is why they were providing base load. We'd have to install far more renewables. So currently, to get to France's carbon intensity, we'd have to go up to 70% renewables. And then with 70% renewables, you have the intermittency problem. So how do you deal with, well, you know, it's dark overnight, so the solar ain't working. And sometimes the wind doesn't blow. So then you need energy storage. You know, and actually the key issue is, how do you get the energy storage in place to take advantage of excess renewables? You know, you have to think of a new way of managing the grid. It's the answer to all of these questions is it's complicated.
Yeah.
We
don't think enough about energy storage, actually, and that's
we got to. But the other thing is the assumption that again renewables don't come with a zero burden.
No.
When we look at wind, we get a pretty good return for the energy invested, the energy that we recover. But photovoltaics, it's not quite so simple. And photovoltaics are something. I mean, I'm not saying we shouldn't have them, but I think we should think very carefully about them. People seem to think they're a panacea. When first of all, it takes enormous amounts of energy to create photovoltaic modules, and then at the end, what are we going to do with these doped semiconductor materials? And I think that's something we haven't thought about at all.
Callum, I'm going to ask a question for you. You started to explain the difference, and I think I probably muddled it up in my talk, the difference between an embodied and embedded.
Yeah, no,
dreadful.
Guilty as charged. I said
Yeah.
embedded when I meant
Yeah.
embodied.
Yeah, this happens a lot, and so I thought I'd dwell on it a bit. The best thing is to not use the word embedded at all and use inherent. Embedded means if I've got a piece of wood and I burn it, that's the embedded energy that I recover. If I get a piece of wood and I plane it, I saw it, I put wood preservative in it, I don't recover those energies. They've been used to make the product from its natural, to convert.
Worse still if you drive it long distance across the country, yeah?
Yeah, it depends how you do it.
Yeah, where you draw your window.
The answer with everything in LCA is it all depends, which is great. But that energy, I don't recover. That's energy that exists as a kind of an accounting thing. So it's a bit like money, doesn't really exist, but it's a convenient measure of something. So.
Thank you. Yeah. There's a question here from Janice Barton. I agree there is a discussion about repurposing large composite structures and designing for reuse, but what happens when the bus shelter or cycle shed is no longer required? More importantly, for the wind turbine blade, a design that retains the strength and stiffness but uses less material is something. So the question ends there, but I guess you've got as much as you need, really. So, you know, what I guess, you know, you'd have to cascade further. I don't know. Anyway, how do you want to answer that? Do you want to answer that, Callum? Yeah,
I'll have a first stab at it. I think size does matter when it comes to recovery. I thought about aluminium and its use in aeroplanes and aluminium and its use in drink cans. It's quite easy to, well, most of the time you can recover aeroplanes. You generally know where an aeroplane is. I'm not saying you always do. Drinks can, it's not so easy. So as you go down in the scale of things, this dissipation problem gets greater and greater. And silicon chips are a fantastic example of that. I mean, they've got a tremendous amount of energy that's gone into making them. Trying to recover them at the end of life, because they've got tremendous utility and value, even when they're out of date. That isn't part of the life cycle thinking at all. So it becomes a bigger problem. The smaller the object gets, the bigger the problem of recovery and reuse.
Again, I guess this might be for you, from Mike Hinton. On the glass versus carbon fiber choice, is it not the case that carbon fibers allow the designer to make longer blades and increase the power output of the single word?
Yeah. I mean, that's where we have to make the balance. I mean, in our particular case, it isn't going to be a problem. For the wind turbine blade, for the bridge, it is, because actually the bridge that we're looking at is constrained because of its weight and stiffness per the unit span to have carbon in it. So in that case, we're not making a comparison between glass and carbon. We're making a comparison between steel and carbon.
Yeah, I mean, the qualifying thing here is not possible to make viable glass reinforced plastic blades at the very high power outputs.
Yeah, I mean, you know, that's where the balance comes out. Generally speaking, as I say, when you look into LCAs of wind turbines in more detail, we're just looking at the blades in this project. You'll find the blades are pretty insignificant, actually.
Yeah, and are there opportunities for using additional manufacturing methods such as water jet cutting or conventional machining to extract smaller scale parts from larger parts?
Sure, I don't know the answer to that, and I'm sure Tony does.
Yeah,
I guess there is. I mean, actually, composite joining is an issue. Actually, making larger parts out of smaller parts, you know. So having the modular composite system, but being able to join as well as disassemble.
Joins and surfaces, the nightmares of material scientists.
Yeah. So how do we build a more expansive and reliable LCA database? Whoa, well.
You've got to spend more money on LCA practitioners.
Yeah.
It's coming, but it takes time.
And you hit on a good point. Sorry, Tony.
So the other thing we need is kind of agreed methodologies. So not only does there need to be a more expansive database, but we also need to have verifiable and agreed calculation methodologies, so that one person's LCA and another person's LCA come up with at least nearly the same answer.
Yeah, but we're getting there. We're getting there.
Yeah, and again, it's it is an area where there's been some progress, and then incorporating the environmental risk assessments as well, because the two orthogonal things. People have been asking in the chat about leakage of chemicals into the environment. Well, I'm sorry, that's not in the LCA, right? If you want to know whether your microplastic or your diesel particles are harming people's health, that won't be in an LCA.
Yeah, it's not a panacea for everything in LCA. It can give you guidelines around design, and it's certainly better than nothing. It's a bit like the democracy thing in Winston Churchill, that he didn't know of a better system, but it was dreadful, and that's what LCA is. It's a dreadful system that we don't know. It's the best we've got, but it's getting better.
Yeah, sadly, democracy's going the other way.
We're moving on to dangerous ground.
Yeah, one of the world's problems. Thanks for your talk, Callum. Can you shed some light on, this is a question from Will P, whoever Will is. Can you shed some light on why your customers are coming to you for LCA, i.e. why do they care? Is there new legislation on the horizon to force industries to consider sustainability in design? Yeah,
it's very interesting. The landscape's changed a lot, probably over the past 10 years. We were talking a little bit, touching on the introduction of standardization, which is making people use the same methodology. And when people start using the same methodology, it becomes more realistic to compare one thing with another. There's been legislation that's been introduced, particularly within the framework of Europe, to start to report environmental burdens. And because of that, companies have got more interested. And it's taken on a life of its own. It's been very interesting to be part of that process. And also to see, quite honestly, the cost of these things is coming down as a consequence, because there's more people competing for that market. So it's becoming more accessible. You can go now onto websites which have things called environmental product declarations on them, and you can get a lot of information for nothing, which is very, very useful, rather than paying a lot of money to get an environmental database. So there is a lot more activity than there was. Why do companies do it? Sometimes they do it purely as a marketing thing. Other times they do it because they do feel environmentally responsible. So it depends on the individual company.
Question from A Serena. What about Vitrrimer resins to produce composites?
So again, as a composite matrix, it'd work if they work. Yeah. So the whole point of a Vitrrimer is that you make a glassy polymer that has cross links that are labile at higher temperatures. So essentially you make it's a thermoplastic glass.
Right.
But the relaxation times are generally a lot longer than a glass, because when it's in the glassy state, there are covalent crosslinks. But getting around the problems of stress relaxation and creep are difficult.
Yeah.
But no, it's perfectly viable. A whole lot of research. I'd just say to those researchers, the benefit that you get needs to be tested against the extra energy that you need to put in to make the Vitrrimer in the first place.
Yeah. Yeah.
But, I mean, I'm very much of the view of we need to make current chemistry more efficient energy-wise, rather than inventing new, massively energy-intensive technologies that don't actually get you much in terms of performance.
Yeah.
We need to be thinking about the whole life a lot more than we have done. This sort of in-out use of materials, one shot, throw it away. We go to a lot of trouble to make these things. We produce them in very high states of purification with very high performance. Then we use them once and chuck them away.
Yeah. Well, and to come back to your dissipation point, Callum, we go to great extents to make things, to separate things and make them very, very pure, and mix them together again. in very, very small quantities. So, you know,
Yeah.
of the 118 naturally occurring elements, 75 of them are in an iPhone.
Yes, exactly.
You're never going to get them out again.
No. But there's still a tremendous amount of functionality in there that has become redundant, usually for economic reasons.
Yeah.
We need to be able to access that. I'm not sure.
Yeah, we do.
For my kids, it's generally because the phone's fallen down the toilet. But
There's be a lot of phones in your U-bend.
I think this is an embodied energy question. So what's the difference in terms of energy between thermoset and thermoplastic composites?
I have to look that one up.
Yeah. Depends on the thermoplastic, depends on the thermoset.
Yeah.
But that isn't really, the thing is, a lot of these questions get asked on the point of a kilogram. You know, what's the energy per kilogram? But it's the performance that's important, not the weight.
We've got a popular question here. If we look at burying old composite structures to capture the carbon, what about the presence of harmful chemicals, many that will be banned or are banned, leaching into the environment? Tony, I guess that's you.
Yeah. Again, so the key thing about if you are going to sequester carbon by making this year's carbon dioxide into plastic you can bury, then the burying process needs to be carefully curated. And you know, and solve the problem that way. You know, having highly dispersed plastic in the environment will exacerbate those leakage problems. Curation, policy and curation are the key. You know, deciding what you can make and use and looking after it.
Yeah.
You're suggesting something more like a repository, aren't you, rather than burying it in a hole. It's a recoverable, sort of bit like a library or something.
Yeah. If you want something that's 80% carbon, 20% hydrogen, go over there and you'll find that mixture.
Yeah.
So we shouldn't be throwing things away. Never throw anything away. Like my dad.
Yeah.
It's a big shed.
Yeah. No, exactly. Yeah. All those bike bits you took off and want to put.
The truth of it is we don't throw things away. We don't, not effectively anyway.
Oh, there is no way.
Exactly. There's no way. It's always there, right? Yeah.
I'm going to have to go back to my other meeting, I'm afraid.
All right. Yeah. Well, thank you very much. I think it's probably a good time to finish now anyway. So thank you both for such engaging talks, and I hope you come back for the rest of the days, you know, and it's been a pleasure having you, and thank you everybody who's online listening. We've had between 100 and 150 participants throughout the afternoon, which I think is excellent. I hope you've got plenty out of it, but do join us for the remainder of the conference. We as I've said already, we have several days of meeting. If you go on the website, I'm just sharing my screen now so you can see there's an outline program here. So tomorrow we start at 2 o'clock and we run until 4 p.m. and we're going to be looking at sustainable materials in the supply chain in composites. On day 3, on Wednesday, we're going to be looking at sustainable manufacturing of composites, again between 2 and 4. And on day 4, we're going to look at sustainable composite products, so some real systems. And then day 5, we'd really like people to join our workshop, and that's going to be an excellent day. And as I said before, we've got some special guests for that day. We've got Nadeem Zahawi, who's the Minister for Business and Industry, and Richard Oldfield is also for the Chief Executive of National Composite Centre, who's going to come and talk to us. Jane Nicholson, Director of the Research Base from EPSRC. And we actually have a workshop, as I said, in the afternoon, and we're going to have some provocation at the start with a special guest speaker, Zakia McKenzie. She's a former Black and Green ambassador, and she's going to provoke us into thinking a little bit about sustainability. So thank you very much, one and all, and hope to see you tomorrow.